Stickers and hats. So here we have two independent population proportions, stickers versus hats. A study looks at a student preference for a branded hat and collectible stickers. The sample was 75 business students. The statistical question is whether the proportion of students who wear hats, given that they do not collect stickers, is the same as the proportion of who wear hats, given they do collect stickers. Okay, so we're looking at the proportion of people that wear hats given their sticker affinity, right? And so here we have our sample statistics, okay? And so this is important to know about collecting stickers and not collecting. So not collecting stickers versus collecting stickers, that's a categorical binary variable, right? Whereas wearing a hat versus not wearing a hat is, again, a categorical binary variable. That's very different from the two independent population means as well as pair t-tests. Both of those two techniques required some level of quantitative variable being involved, whereas in this situation, both the variables have to be categorical binary. All right, and so here we have the proportion of those that don't wear proportion of those that wear hats, but those that have no stickers, that don't use stickers, and those that do collect stickers. The proportion of those that wear hats. Okay, that gives us the 0.7 and the 0.51. I believe this data is actually correct. So in terms of analysis, we should get the same results finally. So here, the main important thing to know is just the confidence interval from this output, negative 0.44 and the 0.06. With that being said, you should be able to answer the next next 5 questions. At least try to attempt the next 5 questions. Okay. So going back to this plot's actually it's decent. What would be nice if it would also display the number of those that don't wear hats but collect stickers and don't wear hats and do collect stickers. That will provide all numbers in this plot. This makes it seem as if this plot is hard for you to determine the number of variables in this problem. But since we are analytical thinkers, we can, at least I'm telling you, that there are 2 variables, whether they they wear the branded hats or they do collect stickers. Based on that, since the statistical question is framed in the sense of does collecting stickers have an impact on wearing hats, the explanatory variable is going to be collecting stickers, and the response variable is going to be wearing a hat. Okay, wearing hats or not. And again, both of them are categorical binary. All right, so here it says, what is the difference between hypothesis testing standard error and the confidence interval standard error? So there, in terms of 2 proportions. So in terms of hypothesis testing standard error, you assume that the proportion is based off of the actual data. You're going to pull the information together. You're going to pull it just like how you did for your the pooled standard deviation. You're going to pull it together. Whereas the confidence interval, that's based on the weighted product of the proportions. Okay, so here for hypothesis testing, we're going to pull the information together, and this is how we pull it: the frequency of those that wear hats, given don't collect stickers, and the frequency of theirs that don't wear hats, given that they do collect stickers. Wear hats. This is wear hats, don't wear stickers. This is wear hats, do collect stickers. And then the sample size for both, and that's going to be PC, and that's the calculation. Whereas the confidence interval is going to be just the weighted product of the proportions. Okay, a slight difference. So it's important for you to note this slight difference. Okay, state the non-alternative hypotheses. Since we're using proportions, we know that our symbol is going to be P. So our null hypothesis is that P1 is equal to P2, or that P1 minus P2 is equal to 0. Okay, it means the same thing. Okay, so when I say that the difference is equal to 0, that implies that 0 is plausible as a value in terms of the difference. Or in other words, we're saying that same phrase is that P1 is equal to P0. I mean, P1 is equal to P2. And then the alternative hypothesis can also be written in the same manner. Okay, that it's not equal to. All right, so in terms of assumptions, random sampling, independence between the two groups, and at least 10 successes and 10 failures in both groups. That's essentially saying n times p is greater than n times n1 times p1 is greater than or equal to 10. And therefore, we'll do the same thing for Q. And then we'll do the same thing for the second group. So all these have to be greater than or equal to 10 to utilize the Z distribution. Okay. So this is the calculation to find our test statistic, P1 minus P2 minus 0. Again, how far is this difference from 0 in units of standard error? Okay. And then our calculations are based off of these numbers above here, 0.51 and 0.70. Okay, and we get negative 1.377. Our p-value is extremely large, so therefore we should fail to reject our null hypothesis, indicating that there's no evidence the difference in hat wearing proportion between sticker collector, that there is a difference between these two type of people. And if we create a 95% confidence interval, I didn't give you the CV here, but the CV would be 9.6. I think I say that, don't I? No, I don't say it. CV is equal to 1.96. You can see that 0 is plausible for the differences. So you see the the hypothesis test and the confidence interval agree with one another, and that 0 is plausible. Okay. So again, our point estimate is going to be this difference. And then our parameter of interest, again, is going to be this difference, right? Where we're going to use P1 hat minus P2 hat to estimate P1 minus P2. Again, at the bottom of the video, please let me know how difficult this one was. It's pretty straightforward. In the next couple of examples, we'll do this in class on Tuesday and go from there. Thank you so much.